In this lesson, we're going to be talking about wind and water current problems. Okay, the basis of this is that in some situations, you'll be going either with the wind or with a current underwater. And in some situations, you'll be going against the wind or against a current. And what happens is that it changes the amount of time it takes for you to go a certain distance. Okay, for example, if we have a map of the United States and we want to fly from SFO to Boston, going east, you are actually going with the wind. Okay, there's a wind current that helps push you, and you end up getting there in 6 hours. You can actually Google this. It actually takes about 6 hours if you're flying directly from SFO to Boston. When you're going back west, what happens is that you're going against the current. Okay? When you go against the wind, when you go against the current, you're fighting against that pull. So what happens is it actually takes about 8.5 hours to fly back. Okay, even though the plane is traveling at the same rate, it is more difficult to go against the wind, so it takes you a longer period of time to travel back. Okay, so using this analogy, you will be taking a look at two different problems. One is wind problems. This is exactly what we talked about here, where you're flying either a plane, a jet, or a helicopter. Water problems, when you're talking about rowing a boat or swimming, things that go with the current and things that go against the current. Okay, so let's take a look first at wind problems. Okay, we're going to just take a look at wind problems. So for wind problems, you're going to have the rate of the plane and the rate of the wind. These are two different variables that you will have. Okay, and keep in mind that's the rate of the plane, just the plane. You're not factoring in air, wind, anything. So, and a lot of the problems, they consider this in still air. You're not affected by the wind in any which way. So once you have defined your variables, you need to understand that there's rate with the wind. That means that you're going along with the wind. You will be going faster because the wind is pushing you. So you're going to take x plus y to be the rate with the wind. Okay? If you're going against the wind, it makes sense that you're going to be, moving at a slower rate. So you're going to take the rate of the plane or the jet or the helicopter, and you're going to subtract the rate of the wind because you're fighting against the wind. Okay, once you're set on those two things, let's take a look at what happens when you're in water. It's a very similar effect. In water, like you might be rowing a boat or swimming, we're going to define the rate of the boat or the rate of the swimmer as x, and again, that's in still water. You're not factoring in any current. We're going to let the current be y, okay, because the current is flowing at a certain rate. Okay, when you're going downstream or with the current, you're going to have the help of the current. So you're going to add the rate of the current to the rate of the boat or the ship or the swimmer. Going upstream, as you can imagine, fish traveling upstream, they have to fight against the current. You're going to be taking away the rate of the current because you're going slower, because you're going upstream, because you're going against the current. Okay, so make sure you can see that. Regardless of the situation, whether you're talking about wind or whether you're talking about water, you have one very important thing that you must remember. You have to make sure absolutely every single time that your unit measurements are all consistent. If you're talking about hours, you have to make sure that throughout the entire problem, your unit measurements are in hours. If you're talking about minutes, make sure that in every single situation you have converted the measurements to be just minutes. Okay, so you get to decide which one makes sense. Okay, so we're going to take a look here at example number 1. Okay, example number 1 is a wind problem. It says a jet can travel the 6,000 kilometer distance between DC and London in 6 hours with the wind. The return trip against the same wind will take 7 hours and 30 minutes. Find the rate of the jet in still air and the rate of the wind. I'm going to pause to let you write that down. Okay. If you notice, I've gone ahead and circled the unit measurements. You have kilometers, hours, and minutes. Okay, this is key. If we are looking for rate of the jet and the rate of the wind, the rate of the jet and the rate of the wind will always either be kilometers per hour or kilometers per minute. In this case, we have to think which makes more sense. Okay? It will make a lot more sense if we convert everything to hours, because this is already in 6 hours, this is already in 7-hour chunks. So converting the 30 minutes to hours, you have to think, well, 30 minutes, there are 60 minutes in an hour, so 30 out of 60 is half an hour. Okay, so what I'm going to do is I'm going to cross this out, and I'm going to rewrite this as 7.5 hours. Okay, you might have done this before with Mr. Nguyen. Okay, now all the unit measurements are consistent, so we can go on and solve this problem. Okay, to solve this problem, what I'd like for you to do is to set up a table. You can either set up a table horizontally or you can set up a table vertically. But the key, because these are rate problems, you'll be using the rate times time equals distance equation. Okay, so this is the same setup no matter if you prefer the horizontal setup or the vertical setup. Okay, it's the same equation, rate times time equals distance, rate times time equals distance. Okay, and you're looking at 2 scenarios, with the wind or against the wind. So what I'm going to do is I'm going to read and we're going to go through and fill in the chart, and we'll fill in both charts so you can see the difference or the similarities. First sentence says, a jet can travel the 6,000 kilometer distance between DC and London in 6 hours with the wind. Okay, so everything here is with the wind. Okay, so let's fill this in. You have 6,000 kilometers distance and 6 hours. Okay, so 6 kilometers distance, and again with the wind, I'm going to put in 6,000, and it's going to take 6 hours. Okay, so this is kilometers. That's 6 hours. I don't know what the rate is with the wind, but remember, we already have defined our variables. Wind with the wind is x plus y. So I'm going to put in x plus y. Against the wind, I know will be x minus y. Okay, so let's take a look at the second sentence. The return trip against the wind takes 7.5 or 7.5 hours. So I'm going to put 7.5 hours. And let's take a look at the distance. What do you think the distance is going to be? Well, if you're flying from DC to London and you're going to turn around and go from London back to DC, you're going the same distance. So you can go ahead and fill in the same distance. The distance doesn't change. The cities don't move. The plane moves. And you're moving the same distance. So now that we have our variables filled out, let's take a look at what it would look like vertically. Again, our rate with the wind, you're going to have the help of the wind. So x plus y. Time with the wind was 6 hours. Distance is 6,000 kilometers. Okay, so against the wind, let's 75 hours, and again 6,000 kilometers. Okay, so regardless of what you put in, you will get two equations. Okay, so the first equation, you know that you're going to be multiplying rate times time, and you're going to get distance. So let's take a look at our two equations that we will get. Equation number one, rate times time. Very important. I'm going to go ahead and put in parentheses, okay, no matter what you're looking at, because you're multiplying the entire rate here. So times the time. So the entire rate here times the time will give you the distance. Okay, so that's equation number one. Equation number two, x minus y times the time will give you, again, the distance. Okay, so you have two equations here. Okay, I'm going to go and solve this on a separate sheet of paper. I'll show you also a little trick to make these numbers a lot more manageable. I don't know if you've done this before, but let's rewrite the equations first. So you have x plus y times 6 equals 6,000, and you have x minus y times 7.5 equal to 6,000. So you have these two equations here. Okay, so I'm going to show you this really quick trick. Well, you know that when the parentheses are here, you're multiplying this entire quantity by this number. So what this means is, if you draw your wall of equality, you can divide the left side by 6 and the right side by 6. Okay? You can cancel out the 6. You'll be left with x plus y. 6,000 divided by 6, you'll be left with 1,000. So what we've done is we've gone and we simplified this equation. We can also do the same to the other side, dividing the entire left side by 7.5 and the entire right side by 7.5. What we will have left is x minus y equal to, and I'm going to have to write out this math and make sure I don't make any mistakes. 7.5, again I have to shift that decimal over, and I'll bring it straight up. Okay, 75 goes into 600, I believe about 8 times. 8 times 5 is 40. 8 times 7 is 56, plus the 4 is 60. So that works out. And I still have two zeros, 1, 2. So I'm going to fill in 1, 2. Okay, so x minus y equals 6,000 divided by 7.5, which is 800. Take a look now at our two equations. These are a lot more manageable, okay? And if I actually line them right up, guess what? I can use elimination with addition. Okay? If I add straight down, what happens is the y's will be eliminated because they are additive inverses. Adding the x's, I'll have two x's. 1,000 plus 800, I'll have 1,800. And dividing by 2, x will be 900. Okay, x is 900. I'm going to go in and substitute to one of my equations, and I'll have y equal to, let's go back to our original equation just to make sure. Let's see, this is x plus y times 6 equals 6,000. Okay, I always want to make sure I go back to my original equation just in case. If I divide by 6, x plus y will give me 1,000. If x is 900 plus y equals 1,000, y must be equal to 100. So y is 100. Okay, so now we have to make sure that we answer the question that was being asked. Let's look at the question again one more time. Find the rate of the jet in still air and the rate of the wind. Okay, so the rate of the jet in still air, let's go to where we define our variables. The rate of the jet or the plane in still air is just x. So let's go to our answer. X is 900, And let's take a look at what we should label this. Okay, we're looking at 900 and it's kilometers per hour. Okay, y also is kilometers per hour because look at our distance, it's in kilometers, time is in hours. To get the rate, you're dividing, so kilometers divided by hours, kilometers per hour. Okay, so answering the question, the rate of the jet is 900 kilometers per hour. The rate of the wind is 100 kilometers per hour. And of course, we're going to double check our work. 900 plus 100 equals 1,000, so we're good there. If we take a look at x minus y equals 800, 900 minus 100 does equal 800, so that also checks. Okay, so we've taken a look at one wind problem. Okay, very important. Make sure that you use this as a guide to establish what your variables will be and what you will set as the rate with the wind and the rate against the wind. Okay, so I want you to use this information to attempt this problem. This is an example of another wind problem. A small plane traveled the 1,200 kilometer distance between two islands in 4 hours with the wind. The return trip against the same wind took 5 hours. Find the rate of the plane in still air and the rate of the wind. Okay, please solve this and we will take a look at this when you come back tomorrow. And now I want to move on to an example of a water problem. In this example, you're at Grape Creek, and here's Jim who can row 30 kilometers downstream in 3 hours, or he can row 18 kilometers upstream in the same amount of time. Find the rate he rows in still water and the rate of the current. Okay, so for this example, again, we are going to be setting up our chart. Okay, and you can either, again, make it horizontal or you can make it vertical. Regardless, you'll have the same information in each chart. Okay, and of course, we are using the rate times time equals distance, rate times time equals distance formula. So let's read this carefully and see if we can make sure that we have all the pieces. Jim can row 30 kilometers downstream, so 30 kilometers is distance. This is how far he can row. And downstream, if you're rowing downstream, it's a lot easier. You have the help of the gravity, the current, everything. And so it's a lot faster. So downstream, let's take a look at what we defined our variables again. Downstream, here's downstream, or with the current, this means the same thing. We're going to use x plus y. So with the current, x plus y, Jim can row 30 kilometers, and it says in 3 hours, so let's fill in 3. He can row 18 kilometers, that's a distance, 18 kilometers, upstream in the same amount of time. So it was 3 hours here, it's 3 hours there. Find the rate he rows in still water and the rate of the current. So this was downstream, the other one was upstream. So again, upstream is a lot more difficult. Upstream is against the current, so we're going to use x minus y. X minus y. Okay, so your chart will either look like this horizontally, or you will have with the current x plus y against the current x minus y. Time is the same. Distance, x is 30 kilometers with the current, and only 18 kilometers against the current, because that's a lot more difficult. And again, we are going to be multiplying rate and time to get our distance. So really important. I always want to make sure I put my parentheses in so I don't forget that this is one term. Okay. So when I multiply, the first equation I'll get is 3 times x plus y equals 30. And the second equation I'll get is 3 times x minus y equals 18. I'm going to use this same trick to solve, but I need some more paper. So let's try this up here. So first equation, 3 times x plus y equals 30. And 3 times x minus y equals 18 is my other equation. I'm going to draw my wall, divide by 3, so that cancels out because these are factors. You can cancel factors. So x plus y will be equal to 10, dividing by 3, x minus y is equal to 6. Let's line them up, and we can add to eliminate. 2x would be equal to 16. Dividing by 2, x will be equal to 8. Okay, if x is equal to 8, x substitute in for 8, for x I mean. So 8 minus what number is going to be 6? Y is going to be equal to 2. 8 minus 2 is equal to 6. So we have a value for 8, for x, and we have a value for y. Okay, let's go back and read the question to make sure that we're answering the question that's being asked. Okay, so let's take a look. Oops. Okay. So the problem asks for how far, what is the rate that Jim is swimming in still water, okay? So, or that he is rowing in still water. Can't find the problem, but you have it written down. So we can say that Jim can row, and again we need to figure out what the unit is going to be. Here we have kilometers, in time we have hours. So when we solve for rate, we said distance divided by time, so kilometers per hour. So 8 kilometers per hour with the current, and 2 kilometers per hour against the current. Okay, but reading this closely, I realized that I didn't answer the question that was being asked. Okay, the question that's being asked is, that's not right at all. Guess what happens when I don't read. Okay, I'll solve this problem on a separate sheet of paper. So we have 3 times x plus y equals 30 kilometers, or 3 times x minus y equals 18 kilometers. Okay, so I'm going to simplify this by doing the same trick as the other problem. I'm going to divide both sides by 3 because 3 is a factor, so you can cancel those out. Here I'll have 30 divided by 3, which is 10. Doing the same thing to this equation. I'll have x, oops, I wrote 3, I meant to write y, minus y equals 18 divided by 3 will be 6. Okay, and I can just line these two equations up. Add straight down, I'll have 2 x's, y's will be eliminated, equal to 16. and dividing by 2, x will be equal to 8. Okay, I'm going to substitute in 8 minus y will be equal to 6. Well, 8 minus what number equals 6? Y must be 2. Okay, so I have x equal to 8, y equal to 2. And if you remember, x represents the value we had set for the rate of the swimmer, or the rate of the boat. Okay, in this case it is a boat that he's rowing, so we can say that Jim, let's see, Jim is rowing at a rate of 8 kilometers per hour in still water, and the rate of the current, let me move this up, is 2 kilometers per hour. Okay, so now we have solved for both variables. Okay, so the rate of Jim's rowing is 8 kilometers per hour, and the rate of the current is 2 kilometers per hour. Let's check our work. We have 8 plus 2. 8 plus 2 is 10. Let's see, 10 minus 2 is 6, so we are, or 8 minus 2 is 6, so we are good there. So we've checked our work, we have defined a variable, solved, everything's all set. So what I'd like for you to do is practice a wind problem on your own. A water problem on your own. You'll have this problem. In Prairie Dog Creek, Jerry can row 60 kilometers downstream in 4 hours, or she can row 36 kilometers upstream in the same amount of time. Find the rate she rows in still water and the rate of the current. Okay, so bring this problem with you tomorrow and we'll go over any questions that you might still have.